Jnanam paramam dhyayam. Knowledge is supreme.
In the last lecture, we began our study with the polynomials, more precisely polynomials over a commutative ring. And the notation we have used is the set of all polynomials with coefficients in the ring A is denoted by AX. This is, and we saw again that it is a ring, and this ring is called a polynomial ring over A, and A was commutative ring. And we saw how to add two polynomials, how to multiply two polynomials, and with those binary operations, this is again a commutative ring with multiplicative identity, and multiplicative identity is the constant polynomial 1. So if f is a polynomial, capital F is a polynomial with coefficients in Ax, so f we can write it as A0 plus A1x plus an x power n. This n is the degree f, where an is the last non-zero coefficient. This an is also called the leading coefficient of f, and we capital F, and we call f monic if an is a unit in A. Now let me recall little bit, since I said unit, let me recall few facts about this. So in general, this we will need it later also, so I would prefer that we get acquainted from the beginning. So whenever I have a ring A, remember ring for us is always commutative. So I will not keep saying, all throughout this course we will only consider commutative rings. And that means what? That means A plus is an abelian group, and A dot is monoid, and plus and multiplication are compatible. That means distributive laws. They satisfy distributive laws. So the neutral element with respect to addition is 0, and neutral element with respect to multiplication is 1. That is how we have denoted. So I am not going to make a fuss to write 0a and 1a. So this means they are identity element with the respective binary operations in A. Now this monoid A dot, see this is an abelian group, so every element is an inverse. So in this monoid, some elements are invertible, some elements are not invertible. Now what does invertible mean? So more generally, if M dot is a monoid, monoid means it's a binary operation, associative binary operation, and there is a neutral element with respect to that binary operation. Then I will denote M cross, M upper cross. This is by definition all elements X of M such that X is invertible in M. What does invertible means? So that means, invertible means an element X in M is invertible if there exists an element Y in M such that X times Y equal to Y times X equal to the neutral element E. So this E is the neutral element in M. Such an element is called a neutral invertible element in M, and the set of invertible elements is denoted by M cross. So it is clear that this M cross is a subgroup of M. So what does that mean? That means the same binary operation of M induce a binary operation on this set M cross, and with respect to that binary operation it is a group. So that is obvious, because what do you have to check for this? We have to check that the neutral element belongs to M cross, which is clear. Also, if X is in M cross, then the inverse is the unique element, that Y. See, this Y is unique, and then Y is called the inverse of M. So then the inverse of, so that this Y is called, Y is unique, and it is denoted by X inverse. X inverse. So this is in the multiplicative notation. When you are using an additive notation, then the inverse will be denoted by minus X. So this is also in M cross. Two elements, if X and Y are in M cross, then XY is also in M cross. So if what will be the inverse of XY? Inverse of XY will be precisely XY times Y inverse X inverse, because of associativity. This is X, Y inverse X inverse. This is identity, so it is X E X inverse, but this is X inverse, which is E. So this will be the inverse of this. So that check this. This is obvious. This is also clear. So this is a subgroup of M cross. So how do we test some ring is a field or not? So note, now it has become easier to state A is a field if and only if this A cross is the unit group of, this is called a unit group of M. So A dot and then the cross, this monoid, and take the cross of that. So I just want to just say it here that this M cross is called the unit group of M. So when you have a ring, you have two binary operations, addition and multiplication, and with respect to addition it is already a abelian group, so we don't have to worry, every element has invertible. With respect to multiplication is the only complication, because if the elements are not invertible, we cannot cancel them easily. For example, in ring of integers, only two elements have multiplicative inverses, 1 and minus 1. So it is very important to study a monoid, multiplicative monoid of the ring, and take the invertible elements in that, and that is a subgroup under multiplication of M. This subgroup is called unit group of A. So, when it is a field, this unit group is the maximum possible. That means this one has to be equal to all non-zero elements. Then only it is a field, because this means that every non-zero element is invertible. And remember that 0 you cannot hope to have inverse of 0. 0 is its additive identity, so you cannot hope to have inverse. So these are the maximum possible. So for example, let us see some examples. For example, if you take ring of integers, if I take ring of integers and take the unit group, so I don't have to assume now, I don't have to write in the notation that I am talking about a unit group with respect to multiplication, because with respect to addition everybody is invertible, so the question doesn't arise. So these are precisely plus minus 1. It is a nice exercise for you to find out for any n, natural number n, what is the unit group? Zn cross. These are precisely all those remainders. So all those I bar, or let me call it A bar, such that A bar times B bar is 1 bar. But you will easily see that these are precisely all those, this you can identify this set, all those A bar such that GCD of A and N is 1. I want you to check this. Check this. So therefore, order of the unit group in the first example is 2. Order of this unit group, order, that is cardinality of Z n cross, these are precisely all those integers between 0 and n which are relatively prime to n, and you know that is precisely phi of n. This phi of n is called Euler's torsion function. Okay, so field to study equations, solving equations over an arbitrary ring is, as I shown you in last lecture, that when there are elements in the ring which are not invertible with respect to multiplication, they cause lot of problem because we cannot cancel them easily. Therefore, we are going to concentrate only when the coefficient ring is a field, and last time I gave some examples of field and I will give you still more examples, but today I will continue our study of polynomials still more. So let me formally also define when you say integral domain, that means it's a commutative ring and satisfying the property that whenever I have two non-zero elements in the ring A, B both non-zero, then their product should be non-zero. So this means also, this is also said free from zero divisors. Then you call it an integral domain. That you can test it again by using the multiplicative monoid very easily. This is equivalent to saying if you take A minus 0, this is a submonoid of the multiplicative monoid A dot. Under the multiplication it is a submonoid. So that is because if I have two non-zero elements, their product is again here. So it is a closure property that is very important. In general, this is not a submonoid. For example, if you take if you take Z mod 4, these are, remember notation, 0 bar, 1 bar, 2 bar and 3 bar, because these are precisely the remainders, possible remainders after dividing by 4. And in this, 2 bar times 2 bar is multiply 2 and 2 as usual and take the remainder after division by 4, which is 0 bar. So 2 bar times 2 bar is 0 bar. So when I remove 0 from Z mod 4, it is not closed under the multiplication. Therefore, Z4 minus 0, this is not a submonoid, not submonoid of Z4 dot. And then you can write down many examples like this. So remember our example, we are going to eventually concentrate on, I will have a field K is a field, and we will take all polynomials with coefficients in K, that is Kx, and this is clearly an integral domain. So to check this, what do we have to check? If I have two non-zero polynomials, both non-zero, then the product also should be non-zero. This is what we need to check to justify that it is an integral domain. But that is, because you see here f is non-zero polynomial, so it has a leading coefficient. The degree is n. Degree may be 0. The constant polynomials precisely have degree 0. G is also looking like this, B0 plus Bm xm, where m is the degree of G, and this An is the leading coefficient LC of f, and this Bm is LC of G, and what will be our multiplication will tell us that f times G, the top degree term will be precisely An Bm times x power n plus m plus the lower degree terms. So this is the highest degree term. So leading coefficient of f times G is precisely An times Bm, and because we are in a field, K is a field, if I take two non-zero elements, this is non-zero, this is also non-zero, two non-zero elements, then the product cannot be 0 because we are in a field. Fields are integral domains. So therefore this cannot happen. In fact, we don't even need for this, we don't even need K to be a field. It's enough that it's an integral domain. That is what we have used. So in fact, we know if A integral domain, then what we have proved is Ax is also integral domain. Then what about in this case, what about the unit group? That is also very easy now. So just let us check that if A integral domain, then what will be what is a polynomial x and then the unit group. That means what? What is this set? This set is precisely all those polynomials with coefficients in A such that this f is a unit in Ax. That means there exists G in Ax such that f times g equal to the multiplicative identity in this polynomial ring, which is the constant polynomial 1, and which is, I will not write this, no need to write this, so I will write in a bracket, that is also g times f, because our operations are commutative, so we do not have to bother about this. So all those polynomials, we want to know what are all polynomials with coefficients in A for which there is another polynomial g, so that f times g is 1. But it is clear that this is precisely, this condition will force what? If I compare the degrees, degree of f times g equal to degree of 1, which is 0, degree of 1 is 0, it is a constant polynomial. On the other hand, we know that degree of the product is degree f plus degree g, because the leading coefficient of this product polynomial is precisely the leading coefficient times this. So, therefore, this is called the degree formula, and that equality happens because of our assumption A is an integral domain. So, therefore, but then which, if the degrees are 0, then that means f is also should be constant polynomial, and not only constant, but the non-zero constant. So, therefore, this is precise, this set is precisely A cross. So, this will mean, this means f is non-zero constant, f is in A and f is non-zero. So, therefore, the unit group will not change if you take a polynomials. So, that is same as unit group of A, and we will, I will, as the course progresses, you will see the information which comes from unit group is very, very important to deduce many consequences for the good results. Okay, so now the most important thing that we have been using in our school days, I want to recall a couple of things about that. So, for example, in the ring of integers, I have defined you what are the prime numbers. P is the set of prime numbers, and P we are considering a subset of n. That simply means, when we say prime number, that means by definition we assume them they are positive. So, this is the set of prime numbers. Okay, and we have seen that they are infinite, they are infinitely many. This set is infinite, that we have seen Euclid's proof, that there are infinitely many prime numbers. And not only that, we know that, so what was the definition of prime number? The only divisors are, so a number n, positive number n. So, that is a natural number n is called prime if the only divisors of n are 1 and n. And when I say divisors, we should better write in n. This is very important, writing like this, because you see minus n is also divisor of n, if you allow me to go divisors in z, or if you allow me, if I go in rational numbers, then anybody will divide n, because I am allowed to do the denominators. 1 by n will also divide. So, therefore, it is very important to say where you are taking the divisors. So, that is the definition of a prime number. This was told to us in a school. This is not very, this is correct, this is not wrong definition, but it is not good for the future opening. It is not more general definition. So, soon I will define it more general than the definition this, which will work in general ring. This works only in the Z, and not only in Z, it only works in a positive. So for example, if I want to say, let us take our concrete example of this is my ring now, Kx. K is a field. This is what our main interest in this course. And K is an arbitrary field, may not be finite, may not be Q, may not be R, maybe C or arbitrary field. Then when do I say a polynomial F is a prime polynomial? When do I say F is prime? If now I should also define like that about what are the divisors, but now I have to say divisors here. If the only divisors of F in Kx are of the form A times F, where A varies in a non-zero element in a field. So that is A cross, K cross. Remember K cross, because K is a field, K cross is what? K cross is all non-zero elements. That is, and why does it come from? Why does it not appear in this definition of Z? It doesn't appear here because we have banned it. Because you see, what is Z cross? Z cross is plus minus 1. And we made it a shortcut here by taking elements only in N. So that minus 1 got cancelled. Minus 1 was rejected because of this assumption. So it's only 1 and N. So more generally, this is, in this case, this is exactly are the prime elements. This is also not very satisfactory. I will show you as we progress. This K may not be field always. So we should really have a definition in when arbitrary A is arbitrary commutative ring, arbitrary, then what is the definition of, so what is the definition of a prime element? I am just raising this question here so that next time you will be better prepared. You please think about it. What should be the right definition of a prime element in general in a ring? Okay. So we will continue after the break.